Hello everyone. In the previous video we have seen the basics of operational amplifiers. In this video I am going to speak about some aspects of closed loop configurations in operational amplifier, particularly the inverting amplifier configuration. So let us watch it. Now we have seen the symbol for operational amplifier. It has three terminals, the two inputs and one output. So I have modified and made a new circuit where you can see I have added a feedback path from the output to the input, and you can see some added resistors here and a voltage source here. And it is obviously an inverting configuration because the non-inverting input is connected to ground, and we are feeding the inverting input using an input voltage Vi. And this configuration is called a closed loop configuration of operational amplifier. And when you are dealing with a closed loop configuration, we need to understand the concept of virtual short. And the concept goes like this. And suppose the operational amplifier that we are using here is having a very high gain of 10 raised to 6. Then suppose if you are trying to use the operational amplifier in the linear range, that is, this is the linear range. We want to have this in linear range. It should not go beyond the saturation voltages. Suppose your positive power supply and negative power supply are plus 15 and minus 15, then your saturation voltages come between plus 13 and minus 13. So this would be plus 13 and this will be minus 13 volts. So you can imagine, say, a voltage like 10 volts, which is much lower than the saturation voltage here. So it comes around here. Okay, so that is your 10 volt. So suppose if your output happens to be 10 volts, this output is 10 volt, then as per the equation for the gain, you can write output voltage is the product of the gain of the amplifier, the open loop gain of the amplifier, and the differential voltage Vd. So this is the differential voltage, that is the voltage difference between V1 and V2. V1 is the voltage at the non-inverting terminal, V2 is the voltage at the inverting terminal. So that is the difference. And now when we substitute these values, then the differential voltage which is necessary to produce an output voltage of 10 volt will be 10 microvolt. Okay. So this is going to be 10 microvolt. It is a very feeble voltage. So this differential voltage is the reason why we are getting 10 volt here, and for a particular gain, that is 10, if the operational amplifier's gain is 10 raised to 6, then it will adjust the output voltage in such a way that the voltage at these 2 points becomes the same. So you can write here that Vd is equal to V1 minus V2. And what is Vd? Vd is 10 microvolt. Okay, so this is 10 microvolt, and 10 microvolt is a very feeble voltage, and you can approximate it into it as 0 volt. So your V1 minus V2 will be approximately equal to 0, which means V2 is approximately equal to V1. Okay, so that means that whenever you are using this feedback system, then your V1 and V2 will be of the same order, or will be almost equal. There won't be much changes in it. So the difference between V1 and V2 can be practically considered as 0 volts. That means that the potential at V1 and the potential at V2 should be the same. Okay. So this is called virtual short. That means we are trying to connect V1 to V2, somewhat like that. But it is not directly connected, but the effect is in such a way that whatever be the input voltage, the output voltage tries to make a feedback voltage equal to V2, which is almost similar to V1. Okay. So if I am connecting ground potential here, then the voltage at this V2 also will become ground, and that is the effect of output voltage. That is the effect of the operational amplifier. The high gain of operational amplifier makes that effect. In such a way, the feedback becomes equal to the feedback voltage at this point becomes equal to the voltage at this point. So this point is considered to be at a virtual ground. Although it is not directly connected to ground, it has the potential of ground. It has the voltage of ground. So that is why it is considered as a virtual ground. This point is called a virtual ground. And it is to be noted that the input resistance is very high in the case of operational amplifiers. And we have seen that in the previous case. Here this Rin, this resistance is very high, which means that there won't be any current flowing from one point to the other point. There won't be any current. Okay, so that adds to another advantage. So whatever current comes here, it cannot flow into the operational amplifier. So the operational amplifier doesn't take up much current. Okay. So whatever be the voltage that is being applied, the current that is due to this voltage source, that will flow into this point, to the virtual ground point. And there it divides into two branches. One branch goes into the inverting amplifier, the operational amplifier, and the other branch goes to the output through a resistance. And this means that when you connect with the input, there won't be any current flowing into the operational amplifier due to the high resistance offered by the operational amplifier. So whatever be the current that is coming, that will be going out of this junction through R2. So this current that is flowing in this resistance will be equal to the current that is flowing through this resistance R1. And that is our starting point for the derivation of closed loop voltage gain. So let us start deriving the closed loop voltage gain. So we will start with the current that is flowing. So this is the current that is flowing. Okay. So I will call that current as II. Okay. So I need to have another current here also, and that I will call it as IF. That is a feedback current. So according to Kirchhoff's law, II must be equal to IF. You can represent this II as the ratio between the voltage difference at this point and this point to the resistance of the resistor. So it will be like this. So your II will be represented as Vi minus 0. Why 0? Because this point is at a virtual ground. So the potential is 0 volt. Okay. So this is divided by R1. And that must be equal to IF. What is IF? IF is the voltage at this point minus the voltage at this point divided by resistance. So it goes like this: 0 minus VO, the output voltage, divided by R2. And what is VI by R1? It becomes VI by R1 minus VO by R2. So let us take VI and VO to one side. So it will be looking like this: VO divided by VI is equal to minus R2 by R1. Okay. And this number, this ratio, that is called gain. So that is the voltage gain of the amplifier when it is in a closed loop condition. R2 by R1 minus R2 by R1. So this is the closed loop voltage gain of an inverting amplifier, and it is very important. So it says essentially you can make any voltage gain using this amplifier, operational amplifier, by using two resistances, the R2 and R1, and it doesn't depend on the actual values of R2 or R1. It depends on the ratio of R2 and R1. So if I am taking R2 equal to 2 and R1 equal to 1, then my ratio will be minus 2 divided by 1, and that gives me a gain of minus 2. Okay. So that was with the 2 ohm resistance and 1 ohm resistance. Suppose if I am taking a 20 ohm resistance and 10 ohm resistance, I will get the same gain, that is minus 20 divided by 10. So it becomes minus 2. If I am taking 2 kilo ohm and 1 kilo ohm, still I will be getting the same gain. So whatever be the resistance, the ratio of the resistance is the thing that determines the voltage gain. So you are at a convenience of taking whatever be the resistance. So if I want to reduce the value of this feedback current and this input current, I can increase this resistance to 20 kilo ohm or 40 kilo ohm and so but the ratio should be the same. So that is how inverting amplifiers work. Similarly, it is to be noted that if I am giving an input for this, so if I am giving Vi, then my Vo will be equal to the closed loop voltage gain times the input voltage Vi. Okay, so that will give me a output voltage which is equal to minus R2 by R1 times Vi, which says if my input voltage is positive number, my output voltage will be a negative number. Okay, so if this is a positive number, my output voltage will be a negative number. Okay, so the ratio is a negative number, which means it will invert whatever is coming at the input. So if I am having an input which varies like this, and I am trying to amplify it twice, then it will be looking like this. Although there are humanly imperfections in my drawing, still you can understand that the phase of the wave has shifted 180 degree. So this is an inversion of the input. So it is a inverted and amplified version of the input. Okay, and how much it should amplify is determined by the closed loop voltage gain. This one here is the open loop voltage gain, and that is not the case here. It is the closed loop voltage gain, AV. Okay, so that is the open loop voltage gain is given by output voltage divided by the difference between the non-inverting and inverting terminals, that is V1 minus V2, that is VD. So the ratio between the output and the differential input voltage gives you the open loop gain. The ratio between the output and the input voltage here, Vi, that gives you the closed loop gain. So the entire system is closed. If you are going to market this product, then you will be putting this into a box and labeling it and all, and it will be having only two ports, one input port and an output port. So the rest of the system is encapsulated into that box. So that means the gain of the amplifier is determined by the output divided by input, and input can be from your microphone or it can be from your sensor, whatever it is that you are trying to amplify. So that is your input. So what is the ratio between the output and that input that you are going to give, the voltage ratio, that determines the closed loop voltage gain. Okay, and that is fixed by this ratio R2 and R1, minus R2 by R1. So that determines the closed loop voltage gain. And that's all with the inverting amplifier. Thanks for watching, and we'll see the non-inverting case in another video. Thank you all.